The objective is to investigate the type of mechanical engineering for aerospace application, analyze the structure, mechanical properties, microscopic characteristics, method processing, and design limitation for the advanced application.
The problem statement is a specific material must be chosen to fulfill the needs of required applications. The materials must be supported by its structure, mechanical properties, microscopic characteristics, materials processing, and its design limitations.
Regarding our topic, the material for aerospace application, we decided to choose silicon carbide as the material. As an introduction, silicon carbide is composed of silicon and carbon. Another name we call for this material is carborundum. It is a popular option for variety application due to its qualities combination such high hardness, high strength, and high thermal conductivity. One of the application in aerospace application, silicon carbide is applied for high temperature components like heat exchanger, rocket nozzles, and gas turbine engines. Silicon carbide have high melting point and heat conductivity. Besides, it's also suitable to reduce weight of airplane due to the lightweight features. In addition, silicon carbide coatings used to prevent corrosion and wear on metal components. These coatings provide excellent resistance to severe chemicals and high temperature conditions.
Next is the detail on the type of silicon carbide. Silicon carbide is a compound made up of silicon and carbon atoms, and it has a crystalline structure similar to that of diamond. Silicon carbide has several characteristics that make it a promising material for aerospace application. The firstly is silicon carbide can withstand very high temperature without losing its structural integrity or electrical properties. This makes it suitable for use in the high temperature environment found in aerospace applications such as in engine or exhaust system. Secondly, silicon carbide has a very high thermal conductivity which allow it to dissipate heat more efficiently than other materials. This is particularly important in high temperature aerospace application where heat management is critical. Next, silicon carbide has high strength and stiffness which make it suitable for use in structural components and as a reinforcement material in composite structure. It also has a low density, making it a lightweight material that can help reduce the weight of aerospace component and structure. Silicon carbide also has highly resistant to radiation damage, making it suitable for use in aerospace application where exposure to radiation is a concern, such as in satellite and spacecraft. Lastly, silicon carbide is highly resistant to chemical attack and can withstand exposure to a wide range of acid, base, and solvent. This is make it suitable for use in aerospace application where exposure to corrosive chemical is concerned.
Details on the physical properties of the material. Silicon carbide displays a variety of unique physical characteristics. It doesn't have any odor and it has an appearance of black-gray to green powder and gray in solid. This material has a density of 3.2 gram per millimeter, a hardness of 9.5 moles, and a Nook range of 2,670 to 2,815 kg per millimeter. With this hardness and Nook range, this material is harder than corundum, which is the crystalline form of aluminium oxide, making it being the second hardest abrasive material after diamond, cubic boron nitride, and boron carbide. The ceramic is a high-quality refractory material due to its strong thermal conductivity, excellent thermal shock resistance, minimal thermal expansion parameters, as well as high resistance towards corrosion and oxidation. The strong bonding between the silicon and carbon atoms in tetrahedra that make up silicon carbide's crystal structure results in a material that is extremely strong and hard. Up to 800 degrees Celsius, no acids, alkalis, or molten salts can damage this material. Silicon carbide can be used up to 1600 degrees Celsius in air and generates a protective silicon oxide coating at 1200 degrees Celsius. Ceramics made of silicon carbide with minimal to no grain boundary impurities may withstand their strength to temperatures as high as 1600 degrees Celsius.
Next, for the mechanical properties of the material. Silicon carbide has a density of 3.1 grams per centimeter cube, a flux strength of 550 megapascal, the Poisson ratio is 0.14, and its elastic modulus is 410 gigapascal. These are just a few of the mechanical properties which describes silicon carbide as a material. So silicon carbide has a relatively high hardness of 9.5 on the Mohs scale of hardness. This is even harder than aluminum oxide. This is due to its covalent bonding and strong silicon-carbon bonds in the crystal lattice. This is what contributes to its high strength. Although it is tougher than most ceramics, it is still brittle and prone to breaking under stress. This is corresponding to the fact that silicon carbide has a high elastic modulus, which makes it resistant to deformation and stiff. Next, for the microstructure of silicon carbide. On the left, we see a microstructure of a coarse silicate bonded silicon carbide, and on the right, we see a microstructure of a fine-grained silicate bonded silicon carbide. So when it comes to silicon carbide's properties and behaviors, it is dependent mainly on the production methods and its intended usage. Silicon carbide composites can be altered varying in amounts of metals and polymers for a purposeful customization of their microstructure. This is to target specific properties like enhanced toughness or terminal conductivity. In terms of structure, silicon carbide atoms are connected together tetrahedrally, with each silicon atom bonding with 4 carbon atoms strongly holding them in place. Nonetheless, impurities may slip into the lattice system and disrupt characteristics. Polycrystalline silicon carbide ceramics have fine-grained structures that can range from micrometers to millimeters.
Next, I will present the fabrication method of silicon carbide. There are several methods, but I will talk on 5 methods. The first one is chemical vapor deposition (CVD). It's a process by which vapor phase chemicals are condensed to produce solid phase material. The gas combination of silicon and carbon react at high temperature, which will make the silicon carbide to a deposit substance. The methyl chlorosilane will use as a gaseous particle and hydrogen as a carrier gas, then ejected in reaction chamber. The second method is the liquid phase filtering (LPS). It's a method of concentrating powder compared with many ingredients at a temperature above their solidus and consequently with the liquid present. Silicon carbide powder is filtered alongside a liquid phase, usually carbon or boron. The filtering diffuses into the silicon carbide particle and occurs filtering by being heated to a temperature that is below melting point. Grain development and desification and occurs by the liquid phase, creating a high density silicon carbide material with super mechanical qualities. So the third one is the hot press sintering, where the application of the unanswered pressure through simple die shape. The material will be placed in the mold at the 2050 megapascal pressure at heating rate 1600 to 1000 degrees Celsius, resulting in formed material. The fourth is the reaction bounded silicon carbide. It's comprised of silicon carbide powder and carbon sourced with the molten silicon at high temperature. So example, graphite or carbon black infused with the molten silicon at high temperature. This will result in dense and highly durable material compared to the other method. So the last method is the spark plasma sintering method, which in this method the powder sample is loaded in the electricity conducting die and sintered under unanswered pressure. It creates high density and high strength of material at a low temperature around 1300 to 1700 degrees Celsius. So the application of the material in aerospace system. This one is used in the aircraft engine standard turbine blade, short and the combustion linear because it withstands a high temperature. is ideal to use in an aircraft engine. Next, because of the lightweight of the CMC material, it can be used in lightweight components such as aircraft wing and fuselage. Besides that, it also can be used in thermal management in aerospace such as manufacture of heat sink, head spreader, and help to keep the electronic system cool. So the last one is coating. It's a good material to use as coating in critical components such as turbine blades from exposed to the erosion and oxidation. It's more longevity and relies to the wear and tear rather than the conventional coating.
In conclusion, silicon carbide is a structured ceramic material which has the properties of excellent oxidation resistance, strength retention at high temperatures, high wear resistance, high thermal conductivity, and good thermal shock. Hence, silicon carbide is a flexible material which can raise effectiveness and performance of a variety of aeronautical systems. Due to its characteristics, silicon carbide is perfect for high-stress applications while also making it available for electronic and monitoring systems.